Hey everyone, Mr. Armitage here. In this video, we are going to be comparing and contrasting, really, the one proportion z-test and the one sample t-test. Okay. So obviously, right off the bat, we see that they are named similarly. If that didn't occur to you before, we have one proportion. So it tells us how many statistics we are going to be using, how many sample statistics we'll be using. Same thing here, one sample. And then z-test. So it tells us we will be using the z distribution, the standard normal distribution, and the t-test. So we will be using the t distribution rather than the standard normal. And so for each of these, we have certain data or we collect certain things. Right? We have certain statistics for each one. For the one proportion z-test, okay, we have our sample size, n. Okay. We have the number of successes, which is usually denoted by x. And for this, we have our sample proportion, which is p hat. And that is simply x divided by n. Okay? So we need to have a certain situation. Okay? We need to have a Bernoulli trial where we have two outcomes, success and failure. So our situation needs to only have two groups, success and failure. And everything needs to either be a success or it needs to be a failure. Now compare that with the one sample t-test. We do have a sample size, and we still use n for that. But rather than a number of successes, we have the actual data. And I'm going to write that as x1, x2, x3, then it'd be like x4, x5, x6, x7, on and on, all the way up to xn. So we have all of these different values, and there's no single success. Right? There's no sort of way to classify these right now into a success or failure, at least for this particular situation. So from here, we can now calculate the sample mean, which is really the statistic of interest, just like the sample proportion was the statistic of interest before. And the sample mean, x bar, well, you know how to calculate this. Add up all the data, divide by how many you have. Okay. Add up, so sum all of the values of x and divide by n. So these are really what we are looking at. These two statistics are what we are testing. Now, with the one sample t-test, there is also something else that we need that we sort of take for granted in the one proportion z-test. For the one sample t-test, we also have the sample standard deviation, which is typically denoted as S equals square root of, well, it is the sum of all of the values minus the mean squared divided by n minus 1, and the square root of that. Okay. That is the sample standard deviation. Okay. And we actually have to calculate that based on our sample data. Versus the sample proportion, we don't have to calculate it based on the data that we had. It's sort of built into the proportion. Okay. Our standard deviation for the proportion, in this case p hat, okay, which describes our sampling distribution, square root p hat times q hat divided by n. And this comes from the fact that, actually, if I split this up a little bit, square root of p hat times q hat divided by the square root of n. Okay. The square root of p hat times q hat is the standard deviation for a single Bernoulli trial. Divided by square root of n, we now have the sampling distribution standard deviation. Okay. But we don't have that for the one sample t-test. So now let's look at the actual mechanics of the test. So looking at the mechanics of these two tests, okay, to start off with, for the one proportion z-test, we're going to have our estimate of the sample or estimate of the proportion. We are going to have the actual population proportion, and we are going to have the standard error of the proportion, which we can calculate directly from the proportion that we got before. For the one sample t-test, we have the sample mean, x bar. We have the population mean, mu. But now, for our standard error of x bar, okay, the sampling distribution of the mean, it's now S, the sample standard deviation, divided by the square root of n. Now this standard error here, right, I had written it as square root of p hat times q hat, well, actually, which is really sigma, because that is the population standard deviation. It's calculated the same way. Here we have divided by the square root of n. So we see the similarities between these formulae, these formulas. We have standard deviation divided by the square root of our sample size. Standard deviation divided by square root of our sample size. However, the thing is that these are unbalanced currently. In purple, so highlighting in purple here, we have this parameter for the population, and we have this parameter for the population as well. So we have two parameters to specify our population, which is totally fine. However, on the one sample t-test, we have this parameter here for the population, but because S here is a statistic, it is not the population parameter. It cannot be the parameter. And of course, the smaller our sample size, the more unsure or the farther away our standard deviation may be from the population standard deviation. Right? If you think about it for the means, okay? If you have a population and you're taking individuals from that population, their values may be really far away from the average. But if you take a group of people from a population, that average of that group should be closer to the actual population average. And it's the same thing with standard deviation. You have a small sample, the standard deviation of that sample may be, well, really far off. But a large sample, the standard deviation is going to get closer to what we expect it to be. So that's why we cannot use the standard normal distribution for one sample means. Okay, that's why we use the t-test rather than the z-test. But the test statistic is more or less the same. It's calculated the same way, just we compare it to something else. So for the one proportion z-test, right, we calculate a z statistic, a z score, which is the sample proportion, right, our sample minus the population proportion divided by the standard error. Meanwhile, over in one sample t-test land, it's the same, except now we have our t statistic with n minus 1 degrees of freedom. But it's still x bar, our sample statistic, minus mu, our population parameter, divided by the standard error. So they're the same calculation overall. Just what we are comparing them to is a little bit different. Looking at these two different distributions, we can see sort of what the difference is. Over here, our standard normal distribution, okay, our z-score, is what we're used to. Right? We have one standard deviation, two standard deviations, three standard deviations, right? The z values of that amount. And we know that at a certain point, there is a certain probability or area to the left and to the right. For the t distribution, there's something else that we need to specify, and that is the degrees of freedom, commonly abbreviated DF. Okay? So degrees of freedom. Now, degrees of freedom can be a little bit of a difficult concept, but since it's just a function of the sample size, in our case it is n minus 1. Well, what we were saying before about the sample standard deviation being close to the population standard deviation when our sample is large versus our sample standard deviation being far away, potentially, from the population standard deviation if our sample is small, that is what the T distribution captures in its degrees of freedom. It's kind of like how much wiggle room do you have to get away from the population value. So we can see here on this graph, okay, the black line is when the degrees of freedom are infinity, infinite number of degrees of freedom. Okay. And that's because it does approach the values of the normal, the standard normal distribution. Okay. If you have the entire population or very close to it, then yeah, your standard deviation is essentially known. Okay. Your sample and your population standard deviations are going to be essentially the same. But if it's not, okay, if your sample is smaller, like 1 degree of freedom, so that's a sample size of 2, or 2 degrees of freedom, which would be a sample size of 3, or 5 degrees of freedom, which would be a sample size of 6. Okay, they don't go as high in the middle because all of that extra space is in the tails. We can see here the standard normal distribution is practically, it's almost at 0 when we're at 4 or -4. But with 1 degree of freedom, we're actually really far up in comparison. It's almost to about 0.25, or sorry, 0.025, right? It's halfway to that first tick mark there. So there's a huge amount of uncertainty if you have, only 2 things. But other than that, these tests still work out the same way.